So this is the moment that is we're trying to move on from the machine learning to deep learnings. And the first topic was as you can see in the title, is from perceptron to the multi-layer perceptron. The perceptron is one of the key method in classifications, and I expanded the similar concept to multi-layer perceptron. And here what I did is, like here is the geometric meaning of perceptron. What's the meaning of inputs and the linear combinations and nonlinear activation functions, and what's the physical meaning of the weights. And here is a linear hyperplane or separator or divider or classifier, whatever. And here, let me see. Even the XOR problem is one of the famous one. We have only four data points, but they find out that is linear classifier is not able to separate them. So in that case, there's two options. The first one is probably would be thinking about the nonlinear classifiers. What we can do is that probably do kernels to remap the nonlinearly distributed data set to linearly separable case, or you can think of, like here in this case, is more than one linear classifier. So if you buy the second ideas, probably these two, by looking at this one, it's just one line, line 1, and this is line 2, another line. So this is how we combine them together, and just let me see. And you don't have to use a sigmoid functions for nonlinear activation functions. There are many different options, and here is a sigmoid or the hyperbolic tangent, and the most famous one nowadays is ReLU, is rectified linear units. And these are let me see. Yeah, here is we have multi-layers, and I want you to understand if we add more layers, what kind of the influence that we can have, what kind of model that represent. And for each layers, we can add more units or neurons, and what's the physical or geometric meaning of having more neurons in each layers. And I think I fully explained what's basic the concept of them. And another perspective that I emphasize is that it's for the nonlinear problems. It's a kernel. So this is typical problems for nonlinear classifications. We learned that we are using kernels to map the nonlinearly distributed data set to higher dimensions, and have that in that higher dimensions, or the linear space probably will linearly separable. We are hoping that. And in that case, here we do using for the XOR problems using this kind of kernels. This is one of the examples that now it turns out we can, if you find the proper value of the proper function of kernels, we can make it the data set is linearly separable. So in that case, here it's mapped inputs and using kernels. And the idea is that kernel is nonlinear functions, and we learned that is multi-layer perceptron can represent a nonlinear relationship between the input and outputs. So the next step is that instead of having kernels so that the user can define what kind of kernel they're gonna use it, we implement it like this, and we're gonna ask neural net to learn the kernel as well from the data set. So here is It's a feature mapping. And here you can think of as a classifier. So these are the combination of feature mappings and the classification. But when you learn all the weights, they're gonna do update the weights simultaneously. So that was the summary, and think of as this part is the feature learnings, and later part is classification problems. So then what is deep learnings? If you add include more number of hidden layers, it will be deep artificial neural net. So this, and the next thing was is looking at the parameters. Basically, it's we want to know what's the meaning of weights and bias. And here in hidden layers, as you can see, it's you can make it as a linearly separable using kernels in the beginning of the layers. And therefore, we use logistic regression examples to demonstrate it. And here, let me see. I mean, this one was the interesting things. If you plot it here, everything is from 0 to 1 because we use a sigmoid functions. And as you can see here, at this moment, looks like these are linearly separable. I mean, most of them, some of them are violated, but I think it's okay. And if you're looking at the input space, as you can see, since we have two neurons in hidden layers, we have two straight lines to separate it. So that's how you guys supposed to think and supposed to take a look at the each layers and things like that. And we add more neurons here. That means we're gonna add more lines and classifiers and things. And how do you, let me see. So how do you optimize? I mean, training part is actually we want to find and this one is optimization problems. And so as you guys expected it, we're gonna use gradient. I mean, this optimization problems. And of course, gradient is descent. We're gonna use that. So let's see, we have objective functions and the unknowns and the constraint. In many cases, there's no constraint, so it will be unconstrained, the optimization problem. And how do you, since we're trying to minimize things, we're gonna use loss functions, the term of loss functions, instead of using objective functions in the community of neural net. And there are two famous loss functions. For the regression problems, it will be squared loss, and for the classifications, it will be the cross entropy ones. And you guys have seen these things so many times for the classification problems and for the even binary classification, or I mean logistic regressions, or for this one, if you do that, it will be the softmax for multi-class classification problems. So we embedded in the loss functions into the objective functions when you train it. And here, how do you update, how to find proper value of omegas and weights and bias. And again, it's a gradient descent, and it will be multivariate the objective problems. So we will have omega vectors. So instead of, so we're gonna have gradient. So that's why we learned the gradient in previously. So that's how we do that. But the problem is we have too many omegas, and it's gonna require too many computations for each, even for each iterations, right? So there is some smarter way that we can do. So we call it, it's back propagations or backprop, and which is the topic that I'm going to discuss today. So that was kind of brief, the recap that what we have learned and where we at right now. And before I move on to today's topic, which is backpropagations, and before that, I'm going to explain what dynamic program is first. And you guys have any questions?
No.
Okay, so let's move on to the new topics. This is recursive, means it's one of the central ideas in the computer science. And okay, let me take this example first. Let's think, you guys on, I suppose you guys all know the factorials. And what's the factorial of this? It's like, okay, and what about this? So I guess it's 20 and 120, right? And what about, but as you can see here, 5, and this one is, we know that it's a 4 factorial. So I mean, this is 2, 1. And in order to compute 4 factorials, we know that 3 factorial. And we already computed this. And for that, this one is 2 factorial. We know that is 2. So going back to the second bullet point, and it depends on the solution to smaller instance of the same problem. I'm gonna call it sub-problem. So the idea is that, suppose we have the original problem. To compute the original problems, we can split it to sub-problems. It doesn't have to be like 2, but say we can split it. And for this way, we can split it again. And say this is the end of this, so we can compute each without any difficulties. And once we have these values, we are able to compute it. Once we have these values, we can compute it. And since we have these values, then we are able to find the final solutions, which is the problem that we're looking for, which is the original problem. Okay, that was the good thing about it is because we're trying to solve the original problem using computer. One of the biggest advantages of a computer is it's really good at repeating the process. Okay? So that's why when you do numerical computations, recursive is key. The concept that you have to understand, and you're gonna, I mean, you have to use it to make the computation more efficient, right? So another one is that we're trying to define the functions to call itself. So I mean, it's impossible to in the real problems. What do you mean by that? Say with this one, say I'm gonna put the inputs to compute the outputs, but inside these the operations, and it's gonna call the same functions again with the smaller with the sub problems. So we call it, and it's call it another problem. So it'll be like recursive. Okay? That's somehow that I illustrated the recursive algorithms in here. But in many cases, it will be infinite loop. So we have to make sure that if you think about any kind of recursive method, you have to think about the base case. So if we have to set the certain conditions that if during the iterations, if we meet that criteria or conditions, that we have to break it out to get out of the loop. So I will call it its base case. So in the factorial examples, what would be the base case? What was going to be the condition that we can jump out of the loop? Let me say we have the examples here. Say I want to compute 5 factorial. So that's I put the 5, and for that I need 4 factorials, 3 factorials, 2 factorials, maybe 1 factorials. So it will be, this is gonna be the base case, right? So let me see. Another example is of Fibonacci numbers, and so let me see. What will be the F3? What will be the Fibonacci number of 3? If we have this kind of 2, right? What about 4?
3.
What about 10?
5.
What about 10? So okay, so let me ask, in this one, in Fibonacci numbers, in order to compute it, what would be the baseline condition?
One. One.
No,
it's 2.
The condition is that, say this is Fn. I want to compute f of n, right? Then say in here is if, so I want to say the baseline first, if n equal to 1 or 2, then we have to return 1. We don't, right? And break. Maybe say and break, right? Else, if this is the function of f of n, return f n minus 1 plus f n minus 2. Does it make sense? So this one is baseline conditions. And so to compute this guy, we need, so we get, it's gonna call the another functions, which is n minus 1. And I'm gonna check whether n minus 1 is equal to 1 or equal to 2. Else, I'm gonna return f n minus 2 plus f n minus 3. Right? It's gonna repeat it. Same for this guy, for f n minus 2, whether n minus 2 is equal to 1 or 2. I will check it. Else, return the values f n minus 2 plus f n minus 3. It's getting complicated, but somehow the computer is able to figure it out with this kind of recursive method, and we call it it's a very fancy name. It's a dynamic programming. It's very general and popular method to this. I mean, in many cases. Okay. Let's think about how do you compute the Fibonacci numbers in recursive way. I will call it's naive because I'm gonna enhance or improve it in recursive method later on. Let's think about it when n is, for this one, then n is, that means if n is 1 or 2, I'm going to return it, the f value is equal to 1 because that's what this the first equation is telling us. And if n is greater than 2, actually we have to compute it, right? And we're going to return the value of f. Does it make sense?
Yes.
And let me ask, I think it's going to work. But the question is, do you think it's good or not? Do you think it's good or not? Think about the question in the perspective of computer. Do you think it's if you ask these things to computer, do you think the computer is going to happy or not? So the question is, to compute this, as you can see here, to break down the solve problem, so I need to the computer needs to compute these two. And to compute this, there's another solve problems. To compute this guy, we need another solve problems until it meets the break lines. But the question is, you have to see here f of n minus 2 here, and there's another computation. Okay, so that means here you think it's going to be the big branch of trees, and there's another one. So it's a redundant. You have to do just same computations many times. So that's the problem. I mean, it's not a problem. It's inefficient. Any ideas to improve this? So I want to get rid of naive here. I know. I mean, two of you is a major in the computer science, and you guys should say something. So
the value of n rank of computing, because we can see on the diagram that we compute 2 times, for example, f on n minus 3. So it would be less redundant firstly if we store the values.
Let me see. So here the title is, as you can see here, it's memorized. So the idea is that before actually you conduct the computations, you can check whether the computation is done or not, right? If this is already computed, you don't have to repeat it again. So that's why we're gonna set another memory here. And if so first thing is that whether that the value that the value that you requested it to compute the Fibonacci values, or if that's in memory, that means at some point you already compute. So in that case, I'm going to return the value that you already computed, right? If the n is not in the memory, that means it's the first time that you see, then you do just same, you repeat it. This is baselines, and just do the same thing. And once you're done, now since that means here means if n is not in memory memo. So now I'm gonna, because I already here I computed, so I'm going to update it. Now I have n in my memory, so I'm gonna return it. So that means so I don't know which one is first, but say I compute it. In order to compute that, I need to compute these two. And to compute this one, I need to compute these two. So I'm gonna do that and repeat it. So I already computed. So once I'm done this part, probably I'm going to move on the right side, and I'm about to compute this guy, but I know that because I put everything in the memos. So here I know since I already computed, I put n-2 in my memory, so then I don't need to go down. I just return the computed values. So in that case, I do not need, right? So by doing this, the benefit is that it only recurs at the first time it's called. Right? So that's the memorized. It's much faster than the naive recursive or naive dynamic naive recursive method. Okay, so you can think of as this one is space, and the computations is in computation in time. In order to save the computational time, you add more space. So there's a trade-off. You guys know what I'm talking? Okay. So physically you need more memories in your computer. That means you have to reserve more space, right? To reduce the computational time. Sometimes you might be like, I have enough time, but I don't have any money or space. Money to buy memories, so I don't have any space. Then in that case, you have to compromise it, and you're just gonna make use of naive recursive method too, but it's gonna take longer than, right, memorized. Okay, that's the big difference. And what I want to say is dynamic programming is recursive plus memorization. So it's memorized and reuse the solutions to solve problems. So it's going to help solve the problems. We call it, this one is DP problem. So the main idea of dynamic programming is it's a recursive, right? And probably the original problem is big, but I'm gonna make it and split it to make the solve problems. So it's gonna recursive. And on top of that, because I wanna compute only once. So if I already computed, I'm gonna put reserve the values in the memory. So it's a memorization process. So I'm going to combine them together to make faster computations. It's for dynamic programming. Right, that's the main idea of dynamic programming. And let's move. I mean, coming back to the original problem that we have, it's how do you train neural net? What I'm saying is that I'm going to use DP for gradient descent. Okay. This one is, there is a fancy name. It's a back propagations. So back propagation is nothing but, I mean, the purpose is that I'm going to train or find optimization problems to train or to learn all the weights and bias or unknown parameters in the neural net. And the main method is I'm going to use dynamic programming for gradient descent. And let's think about, go back to the original problem. And I mean, we can use a gradient descent method to find, I mean, this is a generic numerical way to solve the optimization problems. But one of the issues for neural is that there are too many weights. Okay. And here, I mean, from now on, in neural net, there's a weight and bias, but I'm gonna say just all of them. I'm gonna just say omegas and the weights. I'm not gonna make it distinguishable, right? I'm just gonna say all the parameters or the weights. And in your mind, you just think of as I mean the weights and bias. And the problem is, say we have, suppose we have, I don't know, I mean, 1,100, 1 million the weights, then you have to, for each iterations, you have to compute all the partial derivatives. So it's too much. So what I'm saying is that here, let's say here at the end you have loss, and I want to know, say this is the omega of 1, and I compute forward propagations to compute it, and I want to know, see whether in the next iterations I need to know whether I need to increase or decrease the value of omega 1. So for that one, I need to compute, and say we have another one, and I need to decide the direction of updates, I need to do another one. Right? That's basically, in theory, it's I mean, we know how to do it, but in practical, it's too much computation. It requires too much computations. Okay, so let me think about what's the uniqueness of here is that we are dealing with the unique structure of multi-layer perceptual or artificial neural net, which means we have layers. Right? There's no connection like this. Let me see. We know that there's no connection like that. There's no connection like that. So it's a uniqueness of MLP is that we have layers, and there's some connections here, things like that. So we are hoping that if we make use of this unique structures of artificial neural net, we are hoping that there might be smarter way of computing all the gradients, or there's some smarter way we can reduce the number of computations that we need to conduct to compute all the gradient. That's probably proper way to say that. And let's think about the forward and back propagation. Forward means that in that directions. So if we all given weights, and if we input is assigned to feed into the networks, we can just do linear combinations and nonlinear activations and many repeated many times, and we will get outputs. And backward, the back propagation is that, let me see, in given outputs, we'll do that way to decide that one, right? So that's looking at the directions of the computations. Forward is in that directions, backward that is that in the opposite directions. And this the opposite directions. If I'm telling give you the answers is related to memorizations. I'm going to explain why I'm saying that in a minute, in a second. So let me see, the back propagation is related to memorizations. So let's think about the back propagations. I mean, here's some, now I'm representing that way, but I'm now in here to explain it in that direction. So I'm thinking this is the inputs and hidden layers, and think about it as outputs. And here all the functions might be different, but I'm thinking all the functions are the same, just for the simplicity, right? So I'm assuming that all the functions are the same. It doesn't have to be different to explain what the back propagation is. And let me see. So this is outputs, and z is function of y. So if the y, the value the value of y is given, and we can compute z. And here y is function of x, and x is a function of omegas. Omega is function of u. I mean, here doesn't have to be the same, but I'm just saying, assume that these are the same. But let me see. I want to know whether, so let's say this is the output or loss. For the minimization, I mean, any kind of optimization problems, I want to know for, I assume that I'm gonna use the gradient descent. I want to know each iterations. Do we need to increase y or decrease for each variables? To do that, I need to compute, right? If this is positive, then in the next iterations, I need to decrease, how do I say, right? And what about the x? Do I need to increase or decrease? I don't know, but I need to compute. So I need to know the relationship between the z and x. But in between we have y. And what about the omegas? Do we need to do? I need to compute that guy. What about the u? I need to compute this partial derivatives or gradient. And okay. Then let me see. So all I need to do is we need compute these. Okay. And let's think about this one it's just, this one is just f prime, Is good. And what about this? Well, z is not a function of x. Z is a function of y. But we know that y is a function of x. So what we can do, right? So I'm gonna, what I did, I just used the chain rules. Because, I mean, here is, if in Euronet, it's layer by layers, and this guy is function of this one. This one is function of that guy. So in the functions, we can think of this as a composition of functions. It's a function of functions and the function of functions. And for the composition of functions to compute the gradient, we have to use chain rules. And to compute the gradient or compute this guy, we need to know that. We need to compute the gradient, two partial derivatives. And let's keep going. What about z omegas? We need to know, because we don't know what z is a function of y, so y is function of x. X is function of omegas. And we can repeat it. U, y, sigma x, sigma omega, sigma u. Okay. And this is, I mean, here is the input, and this is output. In that direction is forward. This one is backward. So if let me see, and now you have to, this is not good colors. This one you can see over there, and these right here, and these right there. So in order to compute all these gradient or partial derivatives, if we are looking at these directions, then you have to compute these and to find out this. And for next step, you have to compute these. But the problem is, the thing is, you already computed. You just repeat the computation again, right? So if we're doing the opposite directions, to compute these values, this one is already computed, so assume that it's memorized. So if we compute this one first, when you're done with the computations and you just put that in the memories, now at this moment, oh, I need to compute that, but if you check it, I already computed, so I'm not gonna compute, I'm just gonna get the values from the memories. All you need to do is, I'm just gonna compute this. So that's the second. And the next thing is that here I already compute these two, and this one is, so I'm gonna read the values from the memories. I don't need compute this. All I need at this step is that just another one partial derivative. That's it. And with multiplication of the values in one of your memories. Does it make sense? So in backward, it's memorized recursive, which is DP, and we call it's a back propagations. Backprop in artificial neural net. So I'm doing that way. I need to compute this, and I need to compute this, but this one is just multiplications, and this one is just multiplication of these two, and this one is just multiplications. You see that? So if you're doing the back propagations for each layers, only thing is that you just compute one partial derivatives and do the multiplication, the multiply with the value you already computed in this layer. Okay. That's how we update all the weights recursively with the memories. So that's the main idea of back propagations, and it's much faster and efficient. And that's how we compute all the gradient. And once we're done, we're gonna update it, and that's one iteration. And basically, we're gonna do like 1,000 times of iterations to find proper value of all the weights. And we call it train the models, or learn the model learned all the weights from the data set. That's how we're supposed to say that. So any questions on related to back propagations? Because I think it's conceptually it's so important.
No, I think it's okay.
Okay. And another good news is that, I mean, if you just heard about the back propagation and once, and you think you understand that, you don't have to worry about the back propagation anymore, because once we set the models and in let's say any kind of optimization solvers, in this case it will be TensorFlow, it's gonna take care of everything. So we don't need to know how we train the models. Okay, but inside here it's a back propagation is embedded. That's how we, right? Now we're gonna train with TensorFlow. It's an optimization process. I mean, same as this gradient descent. And it's not easy to numerically compute all the gradients in the neural net in general, but the good thing is that like a lot of researchers have already done all the hard work of developing numerical solvers or libraries. So there are a wide range of tools, but we're gonna use the TensorFlow. All right? So let's just take a look at this one, and let's see where we at right now. So this will be the review of, so it's starting from the perceptron. So it's a structure building or element block. We have nonlinear activation functions in it with linear combinations. And we're gonna stack the perceptron to form the neural net. And we're gonna optimize it through the back propagations. And for training, let me change the colors. And for optimizations, we can do like, I mean, like here is how do you update alphas, and I mean here is using, I don't know, maybe atom optimizers or whatever. I mean, these two I think I didn't mention it. So I mean, here is regularization is, I mean, I think I mentioned several times when you're talking about the overfitting problem. So we have to think about the regularizations as well, because since we have so many unknown parameters, it's extremely easy that for us to fall into overfitting problems. So we have to think about how to avoid the overfittings even in how do you have to think about how to implement the regularization even for the neural net. And another one is batching. I think this one is like, what about this is a stochastic gradient or batch gradient or I mean mini batch, that kind of things. So these are the big picture of the artificial neural net. I think we pretty covered all the topics. So now I'm gonna, let me see what's, so next topic is implemented ANN in TensorFlow using MNIST dataset. Okay. So I think you guys already know her MNIST dataset because I think I use the MNIST dataset for the one of the previous homework assignment. So its full name is Mixed National Institute of Standard and Technology Dataset. It's handwritten digits. It's a 20 by 20, a 28 by 28. But weird thing is that it's when they store it in the database, it's flattened. It's flattened out, so it's like 784 single column or in that way. So I don't know which direction is, but it's vectorized. So it's not an image or it's not a matrix anymore. Okay, that's the key things you have to remember it. And to say it's 28 by 28. So each pixels have gonna value from, I think value from 0 to 1. It's normalized. I'm not sure. It's probably this one or this one. I think that's the values are normalized, so it's represented that way. And here is the image or matrix, but when they store it in database, it's a 784 the flattened. So what I want to do, I want to implement it. Let me see. Yeah, I want to have neural net for classification problems. What's the input size? What's the input size? What's the input size? Hello?
Yes.
What's the input size for the MNIST dataset problem?
780.
Right. So it's a long column. And how many classes? I don't think it's a binary. It's a 100-digit problem, so we have from 0 to 9. So it's a 10 classification problems with maybe 784 input units. Right? That's the given problems that we need to attack. So if we do one-hot encodings, it will be the number of neurons in the output layers is going to be 10. The input layers is going to be the 784. Now you need to design your networks and see, I mean, these are given, I mean, fixed. These are fixed. I mean, because it's due to one-hot encodings. I mean here. now there are a lot of freedom that you can design it. Say I want to include 5 hidden layers, and each layer is probably, I don't know, 10, maybe 250, say 40, I mean 100. That's, I mean, it's a design factor. It's a hyperparameters that you have to design. You have to decide it. In these problems, I'm just gonna use 1 hidden layer and including 100 units. I mean, this is not an optimal structures. I'm just randomly pick. I'm not sure whether this one is it's optimized the structures or not, but it doesn't matter because I'm gonna demonstrate how we implement this kind of structures using TensorFlow libraries, right? So remember these structures. I mean, once you done with this kind of structures, and the next thing, all you need to do is just implement it in the same structures so that but the TensorFlow can understand. So we're gonna use iterative optimization schemes, and say this one is network, and if you give the inputs, and this will be the y hat, right? But this is supervised, so it's in the MNIST data set, you know the corresponding, the right answer for that. Now you're gonna make comparison, so it will be loss. And this is it's a classification problem, so I'm gonna use softmax cross entropy things, right? And by looking at here, optimizers, what we're gonna do is compute the gradient using the backpropagations. And so in the next iterations, we know how to update whether each race I want to update. It's gonna figure it out. We're gonna increase or decrease for the entire weight. And with updated weights, I'm gonna update our neural net again. And with different the training data set, I'm going to repeat it so many times. That's the basic structure of how we optimize, how we train the networks using the iterative optimization scheme, right? So in that, I'm gonna use the mini batch because it's kind of compromised batch gradient, and between the batch gradient and the stochastic gradient isn't. And there are many optimizers, and here I'm gonna use Adam optimizers. You don't have to use the Adam optimizer, but this is kind of the quite common optimizers, so I decided to use that. So for that, I'm gonna import TensorFlow STF, and here in the gonna provide examples and tutorials in the MNIST data set. So for one-hot encodings, let me see. In MNIST data set, in the training, we have in MNIST, we have train. In MNIST, we have test. There's 2 different method here. For training, the next batch means if you have one is that means in the training data set, they're gonna pick one randomly and gonna put it in the X and Y. And this one is, we know that the shape is, right? And this one is say 10 because it's one-hot encodings. So I'm gonna reshape it to 28 by 28 to plot it. So that's how, okay. And the Y values, it's one-hot encodings, and I'm gonna just say argmax. Let me see. So this one is that, so this is the labels or Y's, and we know this is 1, 2, 3, I mean 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So if we know that this is 3, so what we can do is that use argmax. So I'm gonna pick the index of that. That's how to get out of this one, okay? So now from the MNIST data set, we know how to get the random batches and using the next underbar batch, and it will be, if you put like 50, that means we're gonna get the random, we're gonna select randomly 50 out of the among the training data set. It will be our batch. So I'm gonna, as I mentioned, that I'm gonna use the mini batch gradient descent. So input size is, you can just write it, okay? And number of units in the hidden layers, I'm gonna say 100. It doesn't have to be. You can say 50 or 200. It really doesn't matter. And the output is, 10. And weights and bias, these are as you can see, the TF variables. Those are the, in a sense of optimization, there will be the decision variables, right? So each iteration, it have to be updated. So I'm gonna use TF variables type, and this one is, we have to initialize it. We have to initialize it, and you can initialize all the TF variables with the zeros, but I'm just gonna use the random normal distributions. Just assign any random values. But let me see here. I use this is a dictionary type. So let me see. We have, we have weights and bias, but each we have hidden layers and upper layers and hidden layers and upper layers. That's the way I use it. You don't have to stick with this way to define all the TF variables, but I feel like this is more, it's easy to implement it. So let me see if you have hidden layers and the input layers. How many weights here? You have 7, 84, and 100. So you have to think about all the combinations, right? That's why you have number of inputs and number of hidden layers. So it's gonna be 84 by 100. For the outputs, you have output, and there's another combinations. So it's like 100 by 10. So that's the number of weights. And what about the bias? Bias is a little different. It's gonna give us like that, right? So bias is, this is 100, this is 10. And I think this, some you need to take a look carefully. That's the, basically you put the structure in it. And what about the placeholders? Placeholder is related to inputs and outputs. So here it's input sizes and the output is 10. And what about this? This means it's not determined yet. The reason why, because we're gonna use mini batch, right? I'm not sure how many data set. So it will be eventually it's gonna be this same as batch size. If I decide 100, that means I'm gonna have 100 MNIST data set. So I'm just gonna none, because I haven't decided the batch size yet. But eventually I'm gonna assign it. So that's for the placeholders. And to put them together, let me see. The models now have inputs and all the weights and bias. And the first hidden layers, I'm gonna do, this is X, or I'm gonna do at this, I'm gonna do linear combinations with all the weights, but this one is here is hidden layers. So weights at hidden layers, I just write it this way. With this one is matrix multiplications, and these are the bias in hidden layers. So I'm going to use bias in hidden layers and do additions. I want you to just, I will do the linear combinations, and that's how I supposed to write in TensorFlow. Once we're done, we do the passing through the linear activation functions and using the hiddens and tf.nn, and we have Lelu function. You don't have to use the Lelu, you can use different activation functions, but here it's and hiddens. I have hidden values. And we're done with hidden layers, and there will be the output. And output is we do another linear combinations with, in output layers we have omegas, weights, and with hidden values we do matrix multiplications, and with summation with bias in the upper layers. That would be the outputs. Okay. Now there's no the nonlinear activation functions at the end. Okay. I'm going to return the outputs. It will be the y hat. So next thing is we need to define what will be the objective, what will be the loss functions, and what kind of optimizers that we're going to use. We have to let the computer know. So since this one is 10 classes, multi-class classification problems, so we're going to use softmax cross entropy and atom optimizers. And let me see here, using the X and weights and bias. And if we decide, that's with the functions, and this will be the y hat. Okay. And the objective function is here, is softmax cross entropy with the logics. And this one is predicted, and this one is true labels, and we define as loss. The reason why I don't have any sigmoid functions at the end, because here it's a sigmoid is embedded. Remember when you compute the cross entropy, right? So that's why I didn't include sigmoid at this phase. And here again, I'm gonna use the batch. Let me see, X. So I'm gonna use batch, right? So we have this one is it's vector, because right, I'm gonna get more than one batches in here to compute it. So in order to take the scalar, probably I need to take the mean, right? Mean value of that. So in TensorFlow is we have reduce underbar mean. It's the same as the mean. And this one is it's the scalar values. So I'm gonna use that one to minimize it with the learning rate alpha like that, using the atom optimizer. So here now it's for iteration configurations. Now at this moment, I would say the batch size probably is a 50. It doesn't have to be 50, but this one is the maximum number of iterations, and every 250 times I'm going to print out the value of loss. And that's how put everything all together. And here, I mean, here we have to open the sessions and initialize all the TF variables like this. And for each iterations here, I'm gonna get from the training data set, I'm going to get 50 out of it, and we have 50 training X and 50 train of Y. And to run it, I'm run these optimizations, and we have placeholders in X and Y, and now we put 50 of them into train in input placeholders and put 50 of them into the output. So once we done here, right, and we will get in each iteration we will do gradient descent to find out the better omegas and the b's. That's, and I mean, plotted the things, and as you can see, the loss values is decreasing over the number of iterations. And in order to test and evaluate it, so as you can see, I got the MNIST data set from the test, which never seen during the training process. I have 100. So each one is that I run predict using only training, I mean testing data set. Now I take the argmax values, okay? And I want to see whether these values are predicted values in the labels are the equal or not. And the number of the equals there will be the same as the accuracy here. So out of, I only 4 of them are misclassified, that's it. And this one is, I got, in order to display like this, I got 1 from the test data set, and let me see, to display this is reshape it, and I plot that, and these are the predicted probabilities out of the artificial, and as you can see, this one is the highest values from, which is, if we use the argmax values, probably the prediction is 4. As you can see, these are the correct answers or correct prediction.